Okay. Now, to start this fixing it, now let's go back to the one-dimensional situation. Okay. We want to this part. We're going to start is energy and work. Okay. Now, I'm trying to show you that all these things are some natural extension of our previous knowledge, the Newton's laws. Okay, how can we get the concept of energy and the work from the Newton's second law? Okay, the Newton's second law says that F net equals to ma. Okay, in the differential form, it's F net equals to m dv over dt. Okay. Acceleration equals to dv dt, the derivative. Now, in fact, we already have that. If we know some force, one of the problem, see that our key issue is that if we know the force, and then from the Newton's second law, find the acceleration, and then we integrate it once, we get the velocity function. And integrate it twice, we get the position function. Okay. Please note that this is the key issue in the mechanics. Okay. We always go do all kinds of things like that to integrate the Newton's second law to get the velocity function and the position function. Okay. And here, so we can do it in a general way. Let's look at if we have the Newton's second law like that. Let's first integrate it once. So we should be able to get something related to the velocity. Now let's see what kind of relationship we have. So to integrate it, previously we first get the whole thing like that. So now we can do it in a little bit different way. We multiply both sides with dt. Okay, so we get, and we get F net multiplied by dt equals to m dv. Yeah. Okay. And then we integrate it by just putting integral here. Okay, so I'm not doing this. Okay, this is for the okay. Okay. I want to do this way. So I want to get something related to the velocity. So I want to integrate with dx. Suppose, okay, if the net force, okay, is a function of x, the position. So then I'm trying to integrate it with the position x. Okay. So you can see what we get. So this is the equation. I integrate both sides. So integrate this with respect to x. Okay. And also integrate this side with respect to x. Okay? So I integrate both sides. So we still should have some equation to equal to each other. Any question here? Now, we need to do some manipulation trick with this one. Look at here. If we rewrite the right-hand side, okay? We can write this as m dv dx dt. What is dx dt over dt? Dx over dt, what's that? Velocity. It's velocity, right? Okay. So this is, or okay, m. You can write it m v v. M is a constant, the mass. So you can put it in front of the integral, right? And then you have an integral v dv stuff. And you know how to integrate it, right? This will give you, here let's do the definite integral. From the initial value to the final value, v dv. And so this will be m multiplied by 1/2 v squared from initial value to the final value, right? Integral of v will give you 1/2 v squared. Okay, any question here?
Is that RHS?
Right hand
right-hand
side,
side.
RHS. Okay? So you get this, and this will be 1/2 m v squared subtract 1/2 m v naught squared. Okay? So the right hand side equals to 1/2 m v squared minus 1/2 m v naught squared. Now left hand side, okay, of course we cannot do anything unless we know the exact form of f negative x. Okay, it can be any form. But we can give this whole thing a name. It's called the work done by the force, net force. Okay. So the right hand side equals to left hand side equals to right hand side. I think many of you have seen this equation before, right? This is called the work kinetic energy theorem. The work done by the net force equals to the kinetic energy change. We also give this term the name kinetic energy, K. So this is the initial K. This is final K. So we can also write it as W net equals to K minus K naught, or W net equals to delta K. The change, the work done by the net force equals to the change in the kinetic energy. Okay. So you can see that this important theorem is actually equivalent to the Newton's second law. We just integrate Newton's second law to do that. And once we have this, of course, we don't have to repeat this process. We can directly use them to solve problems. Okay? So this is a work kinetic energy theorem. And okay, so I hope I gave you the idea why we want to introduce these concepts like work and the kinetic energy. And why the kinetic energy, we want to write it as 1/2 mv squared, right? Probably you are going, the first time when you see it's 1/2 m squared, I don't know if you question why I have to put 1/2 in front of them, right? In fact, it's because when you do the integral, you get 1/2 here. So it's convenient we put 1/2 in the definition of the kinetic energy. Of course, you don't have to, because the essential thing is mv squared. Okay. And also, why we want to define the work? Okay, because the integral here. And now, what I would like to say is that this one probably doesn't really look like the work definition you have before, okay, but in fact it's the same. For a constant, you can see if it's a constant force, what we get, if the force is constant, F net dx, if it's a constant, so you can factor out So you get f net dx. But what's this? This is actually from initial position to the final position. So this is x minus x naught, right? F net multiplied by delta x. So you can see for constant force is reduced to the usual definition of force. The force multiplied by the distance. Okay. So that's a definition. But if it's a non-constant force, if it's changed as a function of position, you have to use integral definition to calculate it. Okay. So again, I would require to be able to calculate the work for some simple function. Okay, like the linear function, quadratic function, sine function, cosine function, exponential function. And another thing is I would like to emphasize that formally we can always do this integration, but this only makes sense if you can write the net force as a function of position. So you can evaluate this one. Okay. So if the net force is not even a function, you cannot write it as a function of the position, then it will be useless because you cannot evaluate it. For example, if this is the function of time t, then you cannot do this integral, right? It still exists there, but you couldn't get any number with it. So it's only useful if the force can be written as a function of position, so you can actually get some number from this integral. So, or in other words, you can calculate the work. Okay. And later we're going to see that if the function, the force can be written in some function of other variable like time, we can do something else. Okay. And please also go back to check the drag force. Okay, you can compare with drag force. There we also did the integral, but in that case, the force is a function of velocity. We actually do the integral with respect to v, right? Velocity v. Okay. But it's a similar idea. Okay. Now we have to introduce more definition. The idea here is that we have in this kind of equation, on one side we have the relatively simple stuff, kinetic energy. It's always 1/2 mv squared, some stuff like that. On the other side, we have the work. So it's a work done by the net force, or you can think about it, each force will contribute some work, and then you put them together. So it will be good for us to do more examination for different kind of force, and to see the work done by these forces, different forces, do they have some spatial feature? Okay, so for this purpose, we want to put the forces into two categories: conservative and non-conservative force. For the conservative force, if we calculate the work done by the force, the work may or may not depend on the actual path of the motion. Okay. So if the work depends on the actual path, we call it non-conservative force. If the work, the value of the work, the amount of the work, doesn't depend on the doesn't depend on the path. We call it conservative force. Okay, so here we list all our common forces. So like spring force, gravitational force, they are conservative force. Frictional force, tension, and normal force, they are non-conservative force. Okay. So at this point, probably we cannot talk too much about the definition. Why? How can we actually define what is depends on the path, what is doesn't depend on the path. But here, at least you need to remember what is conservative force and what is unconservative. Okay, two forces are conservative, spring and gravitational forces, and all other forces are actually non-conservative force. Okay, and here you can try to think about. We always do this kind of things, right? When we introduce the kinematics, we also have the distance and the displacement. And remember that if you have initial point I, final point F, distance depends on the actual path, right? That's the distance. Displacement doesn't. It's just a straight line length between the 2 points. So in the physics, we always need to distinguish about that because we have the motion. Between your initial point and the final point, motion may take any path. Okay. Sometimes we focus on the net effect. Sometimes we focus on effect along the actual path. Okay. And another comment I would like to end is that sooner or later you are going to learn the so-called exact and inexact differential. Okay, in your calculus. Actually, so that means differential here takes the derivative, okay, dx dt, okay, or dy dx. Later you are going to learn that. In fact, there are two different kinds of differential. One is called the exact differential, another is called the inexact differential. Exact differential equivalent to the is related to the conservative force here, the path independence, and inexact differential related to the path dependence. Okay, the non-conservative force. Okay, so that's some comment here. So the reason we want to distinguish the two kinds of force because we can define the potential energy for conservative force. Okay? How can we define the potential energy? We say that for any conservative force, Fc, okay? You can call it Fc. Non-conservative force, you can call it Fnc. You can calculate its work. And the negative value of the work, we call it change in the potential energy. So this is the same thing as this one. Okay. It's a definition. Okay. So the potential energy change is the negative value of the work done by the conservative force. So here, I would like to ask you, why don't we define the potential energy for non-conservative force? Okay, so here you can think about the reason we want to define the potential energy. So, if I have an initial point 1, final point 2, the point is that if you calculate the work done by some conservative force from 1 to 2, okay, and then you can define the change in the potential energy. So you say, if I give some number here, called U2, here I can call it U1, okay. So, and the U2 minus U1 will always be the negative WC. Okay. You can see for the conservative force, this definition makes sense. If you follow another path, get another WC. Okay, this is C1, C2. And so in this case, you have negative WC1. And then you should also have U2 minus U1 equals to negative WC2. For conservative force, this is consistent because we say that for conservative force, the work done by the conservative is independent with path. So this work will be the same as this work if they have the same initial point and same final point, right? So this value will be the same as this value because WC1 equals to WC2, right? But now, if the force is non-conservative force, if this is WNC1, this is WNC2. So WNC1 will be different with WNC2. If we still do some kind of definition, so you are going to have two different values, right? These two will be not the same. So what is the actual value for the potential energy at this point and this point? We cannot get some particular value for any particular point. So it's useless. So we don't define potential energy for non-conservative force. Okay. The whole idea of the potential energy, then we can assign some energy for a particular point. Okay. Any question here? So that's why we have the potential energy for conservative force. Now, let's check, look something about the potential energy. Okay, we say that the potential energy is defined as negative WC. Okay, it's a negative work done by some conservative force. And of course, this is negative if you have some force, Fc, you integrate from the initial position to the final position, Vx. So that's a way to calculate the potential energy. And so this equals to U minus U naught equals to negative x1, x2, Fc dx. So this will give you some expression for final potential energy. It's the initial potential energy. Subtract this, or subtract this is the work done by the conservative force. Okay. So that's the way to calculate the potential energy at any point. But here you can see the initial potential energy is arbitrary. You can set it as any value, in fact it doesn't matter, right? Usually we choose a particular point and put it at 0. So please note that initial potential energy is arbitrary. You can choose it. Okay. So similar, like for number to denote some position, in fact, it's arbitrary because you can always choose your initial position as your 0. Anywhere you can choose it as your initial position. Now, if you reverse this integral calculation, you can get a way to find the force from the potential energy. So if you know the potential energy for some system, that is Ux, how can you find the force corresponding to that potential energy? You simply take the derivative. So that particular force is actually the negative derivative of the potential energy with respect to the position. Okay. So you can see in calculus-based physics, all these concepts are just derivative, integral, all these things. So that's very important, derivative and integral. Okay. And so if I give you some simple force or simple you should be able to find the potential energy. If I give you some simple potential energy, you should be able to find the force from that. Okay, both of the process are very important in the real starting of physical system or engineering. Okay, in the classical mechanics, many times you know the force and you have to find the potential energy. And in quantum mechanics, you always know the potential energy instead of the force. So you have to, sometimes you need to do something like this. Okay. Okay. One thing is, it's very useful to talk about the potential energy curve. Okay. If you start some motion, if you know the functional form of the potential energy, so you can try to plot it. For example, this is a particular potential energy function, okay, with respect to time. So it's say at different points you have different value. So if you have some object, okay, some particle moving in this potential, okay, with some particular energy, okay, so this if this represents the total energy of the particle, say it's 5 joule, okay, and then you can say at different points it has some different feature. Like this one, okay, is the particle moving from this side and go to here. At this point, the potential energy is 6 joule, but the particle has only 5 joule energy. So it cannot overcome the so-called potential barrier. So it will turn back. So this is a turning point of the motion. If you have potential, it will turn there. Okay. You can think about the roller coaster. So if you move to this way and go here, it will turn back. Okay. And these points are called equilibrium points. These things. Okay. They are minimum or maximum of the potential energy. And by the way, how can you find the minimum and the maximum of the potential function? Mathematically, what's the way to do that? Take the derivative and to see where your derivative is 0, right? And by the way, you can see that's very reasonable. When you take the derivative, what's that? That's a force. So if you want to see where the derivative equals to 0, you are actually to see where the force equals to 0. And of course, the force equals to 0. That's the equilibrium point. Okay. So again, math and physics match with each other in these cases. So they are the equilibrium, but we have different kind of equilibrium. This one, of course, unstable equilibrium. Okay. The object cannot be stable there. It will go either this way or this way. This one is, of course, the stable equilibrium. Okay, if the object is located here, it can stable there. This one is called the metastable equilibrium. What do we mean by the metastable equilibrium? So this is a minimum, local minimum, but it's not the global minimum, right? So it can stable here, but if you have a large enough perturbation, it can overcome this barrier and go to a more stable equilibrium. Okay, so this is called the metastable. Okay. These things actually has a close relationship with the phase transition. Okay, the structure of the matter is also determined by the potential of the molecule forces. Okay, the molecule potential. So there are some like a equilibrium and mental equilibrium. Okay, so at different conditions they will trigger the phase transition. So from one phase to another phase, go to a more stable phase. But in the normal condition, they can be stabled into a mental equilibrium. Okay, a less stable phase. So why you have the phase transition from gas to liquid to the solid. Okay, so that's potential energy. Okay, let's stop.